So securing the wireless networks, and we've talked about, you've talked about, you've thought about, you know that convenience and security don't always go hand in hand. If it's convenient, it may or may not be secure. Those things, and what we're going to look at here is to try to make our networks, our wireless networks, as secure as we can with these things. This is the same thing without the channel bonding that you saw a little earlier. I have my Spectrum, which is my wireless access point, my wireless router, and then the relay. I don't know, I was farther away from the relay when this one was done, and then a couple of other people that are in the area. The other guy that's on channel 9 actually showed up a little bit after I did this one, and he's still there, still interfering with channel 6 and 11. I'm on 11. I try to get away from everybody else, try to have my channel on. Whatever interferences are the weakest channels that are available to me. You know, in an environment, we're kind of out in the country, not a whole lot of people around, as you can see. But if you're in an apartment building, this can become a real issue as to which channel can you be on, who's where, who's using what, and people don't do the 1, 6, and 11. Oh, let's see, I see they're on 1. Let me get on 2. Let me get on 3 or 4. Not understanding that the only true channels are those, and this is what shows up in the 20 megahertz bandwidth that we need for these things in order to maintain the separation and the no interference that we would have with them. So securing these things, what we want to do, or what we need to do, is identify the endpoints of the wireless connection, what we're connected to, identify the end user, protect the wireless data from eavesdroppers, and protect the wireless data from tampering. All things that we want to do in order to be able to have our wireless extend the range of our wired. The wired, we kind of do all of those things. Identify the endpoint, yeah, we can do that. We'll look at some other security mechanisms that allow that to happen, 802.1x. Identify the end user, you got to log on. Protect the wireless data from eavesdroppers, not such a big deal in the wired network. We looked at switches and where does the data go? How does it go? How does it travel over a switched network? It only goes to the device that it's destined for. We can then protect the data from tampering. If somebody can get onto the wired data, we're going to have a similar issue, but it's much more difficult. The anatomy of a secure connection, if the clients conform to the 802.11 standards, they can coexist. We're still going to use the CSMA CA, coexist on the same channel where we're going to share the time that we're connected to it. And by default, they're not going to see everything. They're not going to be promiscuous. And by default, or by any fault, Windows doesn't allow you to put a wireless NIC into promiscuous. We can do that with a Linux machine. And this goes back to troubleshooting and those sorts of things, monitoring, and you are going to want to do some monitoring of your networks. Yeah, probably want to get a kind of at least a rudimentary knowledge of Linux in order to do those things. Not all connections are going to be friendly and trustworthy. This guy down here sending the passwords back and forth. It doesn't go directly to the destination like it does in the wired. The wired, again, we can see where it goes. We can see the wire. It goes around in this room that I'm in. It goes around the room back to the physical switch port on the router on the backside of me. Doesn't always, not going to be that way with this. The tablet that I have here, when I authenticate with it, it's going to go to the wireless. It's going to go to all the other areas because it's going to be an omnidirectional antenna. So it doesn't always go directly to the antenna. The antenna pattern can affect the range and the area. The antenna pattern will affect if we have omnidirectional or directional antennas, and how focused the antennas are going to be. Where can it go to? Where will it go from to? But also keep in mind that even if we have a directional antenna, as we get farther from the source, the cone's going to get bigger and bigger and bigger, and this is where we get into that the signal gets kind of weaker and weaker and weaker because it's going to get spread out over a larger area out here. Where are you going to be? Are you going to be in the signal cone is going to be, if we're using directional antennas, one of the things that we have to consider. Convenient is not secure. Can't say that enough times. And use the standards to keep the information secure. We have our friend here. His password is my password is NIHAO123. His password is this. We can intercept the signal. If we can intercept the signal, we can eventually crack. Antenna pattern is one of the things that we can consider when we're looking at our wireless networks. And can the bad guys get into the cone that's going to be used for authentication? We should use some type of authentication, and we typically are going to use some type of authentication. You don't have to. We can turn it off. The original method that was open, it's called open authentication, and you go to a lot of places that have open authentication. The McDonald's, the Starbucks, the grocery store, those places probably going to be open authentication. You don't have to put in a pre-shared key, which we call no authentication. We should have something in order to allow us to see or control who connects to the wireless network. The wireless may connect to the corporate network. It typically will connect to guests should only be allowed on the guest network. The guest network is configured such that it doesn't allow access to the corporate network. We only want our authenticated, approved users to be on and the other thing it brings up is the bring your own device, and which is obviously different mess, whatever that goes on with these things. The problem with that is if you allow users to bring their own devices and connect to the corporate network, then their device on the corporate network, you don't have any control over their device. You can't make them have any sort of protection on it. So we get into, do we want to or don't we want to allow that to happen? But authentication here, we talked about association with the wireless access point earlier this morning. In this case, we want the users to authenticate. The users authenticate before they get the association with the access. Lots of different forms. Could be a text string, username and password. We can use different authentication protocols, and we have WPA, WPA2. Whether we use the personal, the pre-shared key, the text string, or whether we use the enterprise authentication, where we can use a Radius server or a TACACS server, something that uses a username and password in order to have people authenticate before they can get on the corporate network, just like you would with a wired connection. SSIDs may be spoofed. The wireless connects to the strongest signal. We've said that a number of times. The rogue access points can be in our system trying to do this man-in-the-middle attack, so that we're connecting to the wrong device, and we don't really want those kinds of things to happen. All they will to prevent in the man-in-the-middle attack, authenticate to the access point first, and have authentication to the access. Odds are that whoever put the rogue access point in there doesn't know what your authentication is, or obviously can't configure your Radius server in order to connect to it. So authentication is something that should be required, and users can authenticate, and we really want to use usernames and passwords to the greatest extent possible to prevent these man-in-the-middle attacks. Man-in-the-middle attack, somebody sets up a strong signal, a closer AP, and people say, oh, that's my SSID, and they get on it and they say, oh, for some reason this didn't ask me for a username and password, although we can map those things obviously one to the other so that we retain the configuration information. This is one of those, you really got to be careful about what is on your network to do these things. They're going to show up with the same name. And that's where one of the configurations was rogue access point detection. Wireless requires security to protect the components and the data. Encryption is going to be the primary security control. Encodes the information so that if it's intercepted, they can't be read. Anything can eventually be, if it is encrypted, it can eventually be. It's just a matter of how much time it's going to take for that to happen for us. Common security standards, WEP, been around a long time. It's not secure, hasn't been secure. You can crack WEP encryption and on a busy access point probably in under 5 minutes. WPA Wi-Fi protected access was an intermediate step. It's actually an improvement of WEP to provide time for the development of WPA2, which uses AES, the Advanced Encryption Standard, which is now the standard that we use for encryption on the network. WPA3 is the new one. It addressed authentication methods, personal authentication, enterprise authentication, and easy connect, all of the things that can be available. WPA2, mandatory use of AES, replaces TKIP. What WPA did, I'm going in the notes to be sure that I say all these things, it replaced WEP. Most common implementation is going to be the pre-shared key, probably what you're using at home. Uses a 256-bit key. So what it did was increase the bit size, the key size. What happened with WEP, and I think it's somewhere around 48 bits were actually being used. It started out with a 64-bit, but progressed to 128-bit. FBI compromised the 256-bit WEP in 2005. RC4 was the algorithm that it used. RC4 has since been compromised. It really wasn't the weak link. It was the way that WEP was implemented. The 64-bit, only about 48 bits of that 64 bits was used for, get back here, the WPA 2003 was an intermediate step. It introduced temporal key integrity, the TKIP protocol, which used a different key in order to encrypt each of the data packets left the device. So it became a lot more secure. WPA2, AES, the Advanced Encryption Standard, CCNP replaced TKIP, so it's going to replace these. WPA3 is the latest, and this is improvements over WPA2. AES is still the encryption protocol. This is put in here to give you an idea of what happens with this thing. What makes the security algorithm secure? We have the plain text, we add the round key, so encryption round, and there are going to be multiple rounds that go on. We have the encryption round here. The sub-byte's going to shift the rows, mix the columns, add the round key, go on to the next round until we get to the last round, which is going to shift the rows and add the key. So it's going to do multiples, and each of them is going to be a little bit different. Over here on the right, the key schedule here, we do 10 rounds with this particular one. The data path, the bytes here, shift the rows, mix the columns, add the key, shift the rows, mix the columns, add the key, and we're going to have a different key for each round. And shifting the rows and shifting the rows and mixing the column would probably confuse me enough, but it's going to continue to do that for 10 rounds, and then add the round key. Each round is going to have a different key, and this is AES. And it's one of those, the way these things work, pretty spectacular. The message integrity check, the MIC, is one of those things that was added with these things. And this is, what if the data was altered in transit? How would we know? We didn't know before. until we had this added this MIC, the message integrity check, and we looked at, I think we looked at the hashing algorithms. That's really what we're talking about here. Is we're going to create a hash. We're going to encrypt the data and the MIC, the message integrity check. We're going to compute the MIC, the message integrity check, the MIC. Think when you see MIC, message integrity check, think hash. The hash, if anything has changed in the data, it's not going to match when we get to the other side. So we can now be sure that what we sent or what we received was actually what was sent from the other side using the MIC, the message integrity check. Protects against tampering, use of a secret stamp, and it's based upon the contents of the data. And again, when you see these things, think hash. So we do the hash. So when they're identical, we're okay. TKIP, temporal is temporary. Temporal is frequently changing. Temporal port numbers or ephemeral port numbers. Temporal, temporary that we're talking about this. Temporal key integrity protocol. Message integrity check adds a hash value to each frame. And the timestamp, kind of a big deal here. It's going to prevent a replay attack. Replay attack where I intercept the data and then I replay, let's say your username and password to get authenticated. The timestamp is going to prevent those replay attacks. The sender's MAC address, evidence of the frame source, to be sure that they match. The TKIP, temporal key integrity protocol counter, a record of the frames that are sent by a unique MAC address, prevent the frames from being replayed as an attack. And the key mixing algorithm computes a unique 128-bit WEP key for each frame. And we're still talking about WPA here, the key mixing, a unique key for each of the frames, and that's going to provide us more security. A longer initialization vector. Initialization vector is the random character string that we're going to start with in the key generation process when we have those. TKIP has been superseded by AES. Let me just leave this one up and you can look at it, and then we will, actually let's do it in there because I want to leave the nice picture up while we go to lunch here. AES implemented in 2003. It replaced DES. It is a symmetric key algorithm, 3-block ciphers. As of 2017, it hadn't been compromised, and I don't think it has yet. CCMP, more secure than TKIP, consists of 2 algorithms, the AES counter mode encryption and then the cipher block messaging authentication code. And what that does is basically change the devices so that it uses the output of one packet to help create the key for the next packet. So it is now lunchtime, and we'll start with our picture. Actually, let me scroll with our picture first, because the key exchange is what we're talking about. There are a number of different ways to do the key exchange. One of them is this way. Let's say we're going to a website, everything coming from us. So we want to go to an HTTPS. On the HTTPS, on the server over here, HTTPS, we're going to have 2 keys. As you know from Security Plus, we're going to have the private key, and the public key. And we know that anything encrypted with a private key can be decrypted with a public key, which doesn't make a whole lot of sense except you use it for the signing certificate when you sign emails. And anything that's encrypted with a public certificate can only be decrypted with a private certificate. So we go here and say HTTPS, whatever this site is. It then sends us its public key. So we get the public key. So now we have the public key from the site. What we will then do is to create a session key, S-E-S-S-I-O-N, session key on our device, and encrypt it with the public key. So we got the session key, Still can't spell it, can I? Session key encrypted with the public key. It then gets sent back over here. So we have this situation here. Now the private key decrypts the public key, and we have a session key on both sides. Both of us now have, each side has a symmetric key. We want to use symmetric keys because they're more secure and they're much faster. Up to, I read some places 1,000 times faster, or at least hundreds times faster. So the symmetric key is going to be what we use. So we use the asymmetric key to create a symmetric key, or to transfer the symmetric key, the symmetric transfer. And once we have that, we use the symmetric key for this session. So it's going to be called a session key. Once the session's over, that key is supposed to be destroyed. And sometimes you see the site say, okay, we think that we did this, but to be sure that it's all gone away, close your browser. So that session key is only good for that particular session. If we recreate the connection, same site, we're going to go through the same process again and create a new session key. So in this one, Alice and Bob are going to have a conversation. Alice has Bob's public key and Bob has Bob's private key. The private key needs to be kept private. That's, private key, private. It should never be disclosed to anybody. And if you lose control of it, then you're going to have to have it revoked, because anybody can now decrypt anything that you have done. So Alice wants to encrypt with Bob's public key, and by Bob's private key we have these things. So we want a symmetric key, and we have the symmetric key in both places. So what's going to happen? Bob's private key, Bob sends Alice his public key, and his public key, who can have it? Anybody, because it's public and you can post it, do whatever you want with the public key, because it's the public key. And when you sign something with your private key, you want everybody to know that it came from you. So that can be decrypted with the public key to say, hey, yes, I did really sign this. This thing is from me. So Bob sends his public key to Alice. Alice creates a symmetric key. Once the symmetric key is created, it's encrypted with the public key, and then gets sent, encrypted here, and gets sent to Bob, who then decrypts it with his private key. We now have a symmetric key. When this happens here, I got Alice's, and we're going to go the other way around. Authenticity. Here we're going to verify the decrypt, actually, Alice's private key. I will pay $500 and signing. Okay, we're going to sign. Yeah, signing is done with the private key. Why? Because you want everybody to know that it came from you. If you signed it with the public key, then nobody could decrypt it. Only you could decrypt it. Or if you signed it with somebody else's key, it would come from them. So we do signing, and signing actually does some encryption. It creates some hashes, does a number of things. So we sign with the private key, and we encrypt with the public key. Over here, after we do the exchange, the key exchange, we can use the symmetric key in order to make the systems quicker. The Galois counter mode protocol, robust authenticated encryption suite, it's the one that we don't really hear a whole lot about, but it's used in WPA3. I guess we will hear a lot about it. Then I'll be honest, I hadn't heard a whole lot about WPA3, just that it is now being used when we do it. So it's more secure, more efficient than the CCNP, which is part of the WPA2, used in WPA3, two algorithms. The AES, the Advanced Encryption System Counter Mode Encryption, and then the Galois Authentication Code, used as a message integrity check. A message integrity check, again, think hash when you see. So comparing the WPAs, WPA, WPA2, WPA3, authentication with pre-shared key, all of them. Authentication 802.1x, all of them. 802.1x is the thing that we're going to look at next. Encryption and MIC with TKIP, WPA only. Remember, TKIP is the weakest of the protocols. It was designed as a temporary measure to strengthen WEP until WPA could be completed, and we could use it. Encryption and MIC with AES, we get yes for WPA and WPA2, and then encryption with AES GCMP, the Galloy counter mode, is a yes with WPA. A number of authentication methods with wireless. Open authentication is the default, and open authentication means that we're just connecting. We're really not doing any of the things that we would think of as authentication. The other one's 802.1x, which is a protocol that's used for both wired and wireless, to where we have to be authenticated before any kind of an exchange can happen. You can use it on a layer 2 switch to authenticate, to do port authentication. It'll stay basically shut down until you get authenticated, and you can't even get an IP address on those things. We can use it to connect to wireless. Use the 802.1x protocol. It's going to take some certificates, depending on which method that we use, some certificates, authentication server in order for that to happen. The extensible authentication protocol, and we have lightweight, LEAP, EAP, flexible authentication and secure tunneling, FAST, protected EAP, PEEP, and then EAP TLS, transport layer security. Each of those protocols can be combined or can be used in an 802.1x. What we're using an extensible authentication protocol is we specify what's going to go on with it. It's a framework, and then we put in, we configure, we invoke what protocols we're going to use, what encapsulation, what encryption protocol, what hashing, what key transfer that we're going to use in order to be able to use these things. Open authentication is the original open access to the wireless LAN. Authentication request 802.11 authentication request for the device before it attempts to associate with the AP. And what this is, again, is what we think of in terms of encryption. It's not got any encryption. Used in a lot of public locations. When you go to the Starbucks or the McDonald's or the library or the grocery store, typically you're going to see open access points are available. Flag to inform users that the data will not be secure. So there is no security in these things, no encryption in these things, these open access points. What can you do to protect yourself? Be sure that you're on an HTTPS connection. The application layer, and this is encryption down the stack. HTTPS, we're going to be encrypted because it's going to do the exchange, the key exchange that we talked about a little bit earlier before we actually do the connection. HTTPS or VPN, one of those things if you're on an open access point. Otherwise, there is absolutely no protection on it at all. The user's got to accept the policy. Typically, we're going to get a web page that says, yep, I accept the policy, here are the policies. I am going to accept the acceptable use policy also, and those are typically going to happen on all these places so that if you do something really bad, they can kick you off of the network, or they can at least go back and say, hey, they said that they would have followed our policies, but they broke our policies, and then they hacked. 802.1x, port-based authentication, controls publicly accessible ports. Once we're authenticated, the client's enabled to connect to the resources based on authorization, AAA. Authentication, when we prove who we are. Authentication, what we can do once we're authenticated, and then accounting what we did while we were connected. Protocols allowed before it's authenticated. And what happens in these things, this thing is this is going to be the wired. We can use it for wired or wireless. The wireless probably a little bit more straightforward than the wired, because in the wireless we know that nothing's going to happen until we are authenticated, either open authentication or put in the pre-shared key, or if we're using 802.1x, put in our username and password and get authenticated. So what's going to happen before anything happens? Protocols allowed before it's authenticated, but let's go back before that. And let's say that we just turned the computer on. The port, and I'm going to do the port, is going to be in what's called unauthenticated state, which means it's basically down. So we're connected, but we're not doing anything. The port is down. Once we authenticate, the port is down. So what protocols, what important protocols are we going to have to be able to pass from one to the other through the system before we get authenticated? And those protocols that will be allowed are going to be the EAPOL, the Extensible Authentication Protocol over LAN, so that it can do the negotiation. If they weren't allowed to go through, we'd never be able to get this port up. CDP, the Cisco Discovery Protocol, is going to be able to go there, and the Spanning Tree Protocol. All of those are still going to be able to go through this port until it gets in an upstate. Once it gets in an upstate, then we're going to add data to it, that we're now fully connected. The other thing that doesn't show up on the list that I'm about to open up is we can also do phone calls. Phone goes through here, so the data things that can go back and forth, the data VLAN that can go back and forth, is the Extensible Authentication Protocol over LAN, CDP, STP. On the voice VLAN, phone calls, voice traffic across it before we get authenticated. Extensible Authentication Protocol, EAP over LAN, Layer 2 protocol. CDP, the Cisco Discovery Protocol, and the Spanning Tree Protocol can all be part of, can go from one to the other, can go from one to the other, can be transmitted through the port before it gets authenticated. And the players in this protocol, we have the client, which is technically named the supplicant. The terms, and there's a couple of terms that you may need. We'll say the client here, but technically or properly, it's going to be the supplicant. And then after that, we're going to have the actual client to do that. It says the Cisco switch controls access to the network. This guy is actually going to be the client, because it's trying to verify that we're real when we do that. And then the last thing that's going to be in the game here is going to be the authentication server, which authenticates the client. So we have the client or the supplicant, the workstation, the authenticator or the client, the edge, the device, the switch or the wireless access point that is trying to authenticate us, and then the authentication server, the thing that we are using. Let me real quick, and this is probably going to be an out of sequence one, but show you I've got an 802.1x done here. We'll look at these again. The system, it's not a whole big configuration that takes. We'll do a show run here after we do enable and do one at a time. I'll show you a lot of things that you can't do. Let me get rid of that down there. The authentication, AAA authentication.1x, default group radius, which says that we're going to use, we've turned on AAA new model, which says, hey, we're going to use something other than the shared password or the local authentication, the local username and password. AAA authentication, we're going to use 802.1x. It's going to be the default. And group radius says we're going to use a radius server to get the usernames and passwords. So we have that .1x, and this is the other one, .1x system authentication control. After that, we go Spanning Tree. So we have to do the new model. We have to tell it, we have to invoke it as our authentication method, and then we have to do system authentication control. After that, we go to the interfaces, the individual interfaces, and turn it on whichever interfaces we want to happen to have that protocol configured on it. And we got Fast Ethernet 02 and 03 here are configured. These guys, one's up and one's down. The reason one's up and one's down is, as you saw in the configuration, both of them have the protocol turned on, the 802.1x protocol turned on, and this is a little bit, I guess, a little bit kind of when we do this. We do have to do a username and password. And I think it's class and class. We'll see here in this minute, huh? Class and class. We have to actually authenticate to the port before the port's going to come up. Right now it's still in an unauthenticated condition is what it's called. I go back here and see if that's the right username and password. Authentication, MD5, class and class. Given a few minutes, there we go. It is now authenticated. So both of these are authenticated. So what does this protocol do? It keeps the ports shut down unauthenticated until we put in a username and password. And this says public ports. We got those out in the waiting room. We got them out in different areas that users that may not be ours could plug in to the network. We can use it with the username and password. Usernames and passwords coming from an authentication server, and in this case it was a Radius server, in order to say, yes, you're one of us. You can authenticate. We'll now activate the port. Once we activate the port, you can get an IP address. Couldn't even get an IP address before that. And then you can access whatever resources that you have authentication for on. The authentication process for this thing is that authentication's been enabled. The following sequence: if the client identity is valid and the 802.1x authentication is successful, the switch will grant the client access to the network. If authentication is timed out while waiting for the exchange of messages and the MAC authentication bypass option is enabled, the switch will be able to use the client MAC address. So there's a number of things. I've got a flow chart here in a few minutes to look at what are the possibilities that we have with this thing. So what this says is that it's timed out, waiting for the exchange of the extensible authentication protocol over LAN messages. What that typically means is that the client, the supplicant, is not capable of doing an 802.1x. This, as far as Windows goes, this is built into Windows since Windows 7, or probably since, XP had to have a separate client. Vista, I think, had it, and heaven help you if you've still got Vista, or if you have Vista or had to suffer through Vista. Windows 7 on up, all of those, Windows 8, Windows 10, all have the client as part of the operating system. So if you have this timeout not capable, it's going to be one of those that you're going to have a pretty old piece of equipment trying to get onto it when you do this thing. The switch will grant the client access, and this is MAC authentication bypass, which says that, okay, if it's the correct MAC address, go ahead and authenticate it, let them in. If it's invalid and the authorization is not successful, the switch will assign the client to a VLAN assigned by the administrator, including the authentication failed VLAN. Two different things are happening here. One is the authentication timed out, waiting for the exchange of the messages, and the other one is we missed it. We don't know our user. Actually, we improperly, the MAC address is invalid and the authorization is not successful, then it's going to be timed out. If the Radius server is not available, and that's why I kind of caught myself on the one above that. If we don't know our username and password, that's too bad, so sad. We can't get in when we do that. So if authentication, this is authorization, is successful, the switch will grant the client access to the network. The MAC address is valid. If the client MAC address is invalid, then it's not going to let us in. If we don't know our username and password, we're simply going to get timed out and get shuffled off to an invalid authentication VLAN that we would have to use. And this says that the grant the inaccessible authentication bypass option. What if the Radius server isn't available? What if the Radius server is offline? What if we can't get to the Radius server? What if the router sends us bad routes, switch ports down, wires bad? There are a number of things that you can probably think of that we wouldn't be able to contact this authentication server. If that happens, what's going to happen is the network is just not going to function anymore, because users still need to get into the network to do their job. And that's what this inaccessible authentication bypass option is all about. If the inaccessible part is the authentication server, the Radius server that we would use, and we can configure a bypass option for it. What then happens is, once the Radius server comes back online, we can configure because it's going to let us in. We can configure the system to do reauthentication. Reauthentication will check to be sure that the correct device user is still connected to, so that somebody hadn't stolen the session. What would happen if we got on with the inaccessible authentication bypass, and then at reauthentication and the Radius server is available, then we'd still have to provide the correct credentials in order to continue the connection. The MAC authentication bypass, this is to set the MAC address to bypass the authentication if we want to do that, which means that if you've got if your MAC address is in the list, is golden, then you're going to get authenticated. So we're going to set the authenticator static, configure the supplicant to bypass the authentication. See, we've got the correct term here, the supplicant to bypass authentication. If it's connected through a particular interface, set the authenticator static to the MAC address, the interface. That's going to do here, and this is on the switch. Configure the supplicant to be moved to a specific VLAN after it's authenticated. This is one of the clever things that can happen with the 802.1x. Once you get authenticated, the switch can then place you on a VLAN that the VLAN that you should be on after you get authenticated. The initiation for this thing, the client or switch can authenticate. Again, what's really supposed to happen is, once we connect the device, the switch or the wireless access point is supposed to send us a query saying, okay, send me your credentials. Then we'll put in our username and password. It'll relay them to the Radius server. Radius server will either say yes or no, and either let us on or not let us on. But in this case, the router or port is enabled to initiate authentication by using the commands here, the authentication port control auto or the .1x port control auto. And that's what we had here. I think it was not the authentication port control auto, but .1x. And Packet Tracer has limited programming for this thing. .1x system default for these things, and then authentication port control auto down here on the interface itself. And then this is the authenticator that it's going to use, and this is the only one that's programmed into Packet Tracer. Authentication port control auto, after we turn it on globally on the device, then we go to the switch and tell it to use the auto for the port control. The other options are to always let in or never let, that are also not part of the programming of Packet Tracer. So can't look at the help and see a whole lot about that. But the commands to do the interface configuration. The switch will initiate authentication when the link changes from down to up. That's when it's going to ask for, if during the boot up the supplicant does not receive the EAP request, then it can initiate the authentication. What it does is say, hey, wake up, send me a request for identity. It sends a start frame if it needs to initiate it. Switch will then send the request, the EAP request identity. The client will respond with the with with an EAP response identity frame. So the process here, we have the router, the client workstation or the workstation here, and it didn't get the request. Theoretically, when we start up, the device here is going to send this EAP request identity. If that doesn't happen, then the workstation will send the start. Once it sends a start, wake up, ask me for my identity, requests the identity of the device. The identity gets sent, Radius access request for this thing. Then it's going to send a challenge. The challenge is a random character string. So the challenge comes back to the client workstation, to the workstation. The workstation will then encrypt the challenge with its password and send it back, and the Radius server is then going to do the decryption to see if it can decrypt the challenge with the stored password. Then we're going to be authenticated. The port's authorized. Otherwise, it stays in the unauthorized state until we log off. Once we log off, the port becomes unauthorized. It becomes unauthorized. The client provides its identity details to the authenticator. Its role as an intermediary begins. The authenticator here, or the client from the supplicant, passes the EAP frames between the client and the authenticator until the authentication turns out to be either a success or a failure. The processes that can happen here are, we have the start that we're always going to have. So we start here, and then the first, is it capable? And let's go to the no first. No is not capable, and this would be something like XP or older. This device is not capable of using 802.1x. So when the process, the exchange process, the ask me for my credentials process times out, I didn't send anything at all. The authentication process times out. Is the MAC authentication bypass enabled? If the answer is yes, we go down here, use the MAC authentication bypass. Is it valid? We go down and it assigns us a VLAN. If it is, the client address is invalid. One other last hope here is web-based authentication enabled. If the answer is yes, use the web-based authentication. Login passed, we get on a VLAN. Login failed. Assign in the guest VLAN. The guest VLAN has little access. Probably access to the internet, those things. And the other one over here is valid. We get assigned to a VLAN. So a number of things that can happen over here if we are incapable. The authentication process times out, so this would be the not capable. Not that I don't know my password, but not capable. Not capable. Don't have a client. XP actually had to have a client installed on it. And then over here, is it capable? Is it capable? And the answer, yes. Start the port-based authentication. The client identity is invalid. Assign the port to a restricted VLAN. These VLANs may or may not, and these all should say if configured. It's not that it's automatically there. It's not that you have to have it. You may just sit there and say, I can't go anywhere. But the restricted VLAN, users that don't know their username and password or don't have one. The guest VLAN for devices that are not capable. They can be the same, they don't. And then we have a done with that. Client identity is valid. Assign the port to a VLAN, and again, the VLAN that's associated, VLAN associated with the username and password. The other thing here is all authentication servers are down, so the Radius we don't have. Anyway, the Radius servers are all down. Then we use the inaccessible authentication bypass, critical authentication to assign a port to the VLAN. So the flowchart, the things that can happen and what can happen, we can either be, the first thing is it capable or not capable? If it's not capable, do we have the other possibilities configured, the MAC bypass? Do we have web configured in order to allow this device to work? If it is capable, the device is capable, two things can happen. We either got a username and password that we know or we don't. If we know it and we log in properly, then the port gets activated, turned on, and then we can use the VLAN that we're supposed to be assigned to. We get assigned to the VLAN. Otherwise, we get put on a restricted VLAN. If we're not capable and none of the other things are configured, then we get put into a guest VLAN. So each of the possibilities for the different authentication and hardware possibilities that we have with these things. One of the things that may be necessary is we're also going to have health checks, and health checks check to be sure that we have our workstation that is up to date with all of the Windows updates, Windows specifically, that we have an antivirus software that it's up to date. If that's not the case with the health check, it can put us on what's called a remediation network where we can go update that information. We can get the Windows updates. We can install an antivirus software or update our antivirus software before we go through these other processes. Extensible authentication protocol is a framework, and a framework means that we're going to go and when we have this framework, we're going to put in the encryption protocol, what we're going to do. And the reason that we may have a couple of them, may have AES here, and we may have 3DES, and maybe some others here. And then we're going to have a hashing algorithm, and the hashing algorithm MD5, and maybe SHA-1. And then we're going to have a key exchange, and this might be Diffie-Hellman or one of the others. The reason that we need more than one protocol is that what if my device or your device doesn't support AES? We've got to do the negotiation and agree upon a protocol that can be used. And that protocol's got to be present on both devices. So once that happens, we're going to use the strongest protocol that's available on both devices, but we're going to have a suite more than one. We can't just say AES because everything might not have AES to do that. We'd love to be able to do that, but that's not going to be something that happens. It has about many flavors, about 40. Defines a set of common functions for authentication, conditions under which the AAA key management requirements can be met, and then it's going to integrate with 802.1x. A number of the extensible authentication protocols: lightweight extensible authentication protocol, LEAP, Cisco proprietary, predates 802.11. It also is no longer used, not supported by Windows client. And authentication server exchange encrypted challenges for mutual authentication. That was one of the advantages. Both authenticate to each other, the mutual authentication. Uses dynamic web keys in MS Chat, Microsoft Challenge Handshake. Deprecated. It was a weak an exploit tool named Sleep or AS Leap, and Leap is the protocol here, allowed it to be cracked. The EAP, flexible EAP fast extensible authentication protocol, fast Cisco proprietary, replaces Leap. Credentials are protected by passing a protected access credential between the authentication server and the supplicant. The pack, the protected access credential, form a shared secret and then generate it by the authentication server and use for mutual authentication when we do these things. It's going to have 3 phases that goes on. The pack is generated and installed on the supplicant, the one that's trying to get on. After mutual authentication, a tunnel is negotiated. And what these things, when we have multiple tunnels, do, they use the first tunnel, create a first tunnel, and then do the negotiation for the protocols that we're actually going to use for the conversation within the tunnel so that the negotiation process is secret then. And then in phase 2, the end user is then authenticated through the TLS, the transport layer. PEAP, Protected Extensible Authentication Protocol. It's a Cisco Microsoft arrangement here with RSA Security. Overcome the extensible authentication protocol deficiencies. We're going to have an inside tunnel and an outer tunnel and outside tunnel. This is again one that we create a tunnel and then do the negotiation of the final tunnel within the first tunnel, the inner authentication and the outer authentication. The authentication server presents a digital certificate. It could be self-authenticated or a signed certificate. If it is a self-authenticated certificate, and I know that's not what this one's supposed to be about, but you need to install the root certificate so that you will trust it, so that you can make this a trusted. I know that because I've messed that up a lot. Presents a digital certificate. In this case, the server authenticates to the supplicant, but the supplicant does not do mutual authentication to the server. Self-authentication, outer authentication is going to happen with these things, and the authentication server presents the digital certificate. We're going to build a tunnel, and then the TLS tunnel is built. The inter-supplicant authentication and the encryption key exchange. Again, we're going to create a tunnel to do the negotiating with, to create the final tunnel that we will use. All of the passing back and forth. Well, we're going to use the negotiating back and forth as to which encryption protocols, which hashing protocols, all of those things, and the key exchange is all going to be done within the first tunnel. Once that happens, when we get the final tunnel, we're going to send the encrypted data through it. We're going to do all of the data exchanges there. The supplicant has the same digital certificates as the authentication server is used. EAP TLS, open standard, considered one of the most secure protocol, uses the same methods as PEAP, the TLS tunnel. Encryption key exchange, both the authenticating server and the supplicant must have X.509 digital certificates. One of the differences between this one and the PEAP is that both have the certificates mutual authentication, so that each of them is assured that the other one is who they. Private key of the supplicant certificate can be housed on smart cards. Difficult to compromise and save outright theft. If stolen, the card can be immediately revoked, and then the private key is encrypted with a PIN. And that's why we have the PIN for these things. The private key is going to be used for the authentication here. It's going to be encrypted. It's encrypted by the PIN, and once we put in the correct PIN, something we know, something we have for two-factor authentication, once we put in the PIN, it's going to decrypt the certificate, and once the certificate, the private key is decrypted, it can then be used for